Okay, so do you see my screen?
Yes, we can see your screen now.
Okay, so this is our second lecture on Gaussian measures. And my aim today is to define what is the Ito-Wiener expansion and discuss the notion of capacity for Gaussian measure. Okay, so I recall that X is a separable Banach space. X star is a dual of this space. And gamma is a Gaussian measure on X. Okay, X star gamma was defined as a closure of the dual space in L2. Also, we assume that the measure is centered, which means that the Fourier transform of gamma has the form of exponent -1/2 L of RL. So here R is the covariance operator. Also, we defined the action of R on functions from X star gamma as follows. So Rg is equal to the integral of g of x, gamma dx. Also, we introduced the Cameron-Martin space, H gamma, that consists of vectors for which the norm, which is equal to the supremum of L of H, such that L RL less or equal to 1. So this supremum is finite. And also we proved that actually this space coincides with the range of R. And also we showed that actually the space H gamma is the space of all admissible shifts, in the sense that if we take a vector from H gamma, then the shift of measure gamma is equivalent to gamma, and if H is not from H gamma, then the shift is singular with respect to gamma. Okay, so this is a short recap what was yesterday, and now let's introduce the so-called Ito-Wiener expansion. Okay, so this is a standard fact that L2 of gamma is a separable Hilbert space. Then it follows that we can choose an at most countable orthonormal basis in this space X star gamma. Okay, and since this is a closure of the dual space, we can choose this orthonormal basis to consist of continuous linear functionals. Okay, so now let's define some polynomials. So the kth Hermite polynomial is defined by this expression. Okay, so these polynomials are defined on the real line for all non-negative integers k. We will see in a second that this is indeed a polynomial. We can, as an example, check that h0 is equal to 1. H1 of x is equal to x, okay, because when we differentiate this exponent, we get minus x e minus x squared over 2. Okay, then exponents cancel, and minus also cancels, so h1 of x is equal to x. h2 of x, one can compute that this is 1 over root of 2 x squared minus 1, and so on. Okay, and having defined Hermite polynomials, we can also define what is a Hermite polynomial on the Banach space X. So we pick some an amount of indices, okay, for each n. Here Ln is an orthonormal basis. So for each n, we pick an integer alpha n, such that we have only a finite number of non-zero integers, and substitute Ln of x into the Hermite polynomial with index alpha n, and then take the product over n. This defines the Hermite polynomial on x. And the importance of this object is that, in fact, these Hermite polynomials, they form an orthonormal basis in L2. So to check this, it is convenient to have the following series expansion. It turns out that if we expand exponent to the power lambda x minus 1/2 lambda squared into the powers of lambda, then the coefficient near lambda k is exactly the case Hermite polynomial divided by root of the k factorial. This expansion can be obtained from the following. So take the exponent minus 1/2 x minus lambda squared, and write its Taylor series around x. Okay, so we will get the following expression. It will be the sum lambda to the power k over k factorial. Okay, so since we differentiate in lambda, we get minus 1 to the power k, and kth the derivative of exponent minus x squared over 2. Now, to get this exponent, we need to multiply both sides by exponent x squared over 2. So let me write it as follows. And this part, it is exactly kth Hermite polynomial. Okay, so we have such a series expansion, and from it we can check that actually the derivative of kth Hermite polynomial is equal to root of k times the k minus first Hermite polynomial. And from this, by induction, we get that indeed all hk are polynomials. Moreover, hk is a polynomial of degree k, and its coefficient near x to the power k is equal to 1 over k factorial, 1 over root of a k factorial. To get this, let's take our series expansion and differentiate it in x. The derivative of exponent will give us lambda e to the power lambda x minus lambda squared over 2. Here we will have the sum of lambda to the power k, okay, with this coefficient, and here we will have the derivative of hk. Okay, now take 1 power of lambda outside and write the sum not from 1 to infinity, but from 0 to infinity. This is on one hand, and on the other hand, we know that the exponent has the following representation. Now, if we compare coefficients near lambda to the power k, we get that 1 over root of k plus 1 factorial h prime k plus 1 is equal to 1 of the root of k factorial hk. So it remains to multiply everything by root of the k plus 1 factorial, and we get that h prime k plus 1 is equal to root of k plus 1 times hk, which is what was what we had to prove. And one more property of these polynomials is that they are orthogonal with respect to the standard Gaussian measure on the real line. So let's just check that the kth Hermite polynomial is orthogonal to all powers of x n that are less than k. So the kth Hermite polynomial is minus 1 to the power k divided by root of the k factorial exponent minus x squared over 2 kth derivative times x to the power n, and the density of gamma is 1 over root of 2 pi e minus x squared over 2 dx. So these exponents cancel, and we get the following integral. Now, if we k times integrate by parts, yes, then we will transfer this the derivative of exponent to the kth derivative of x to the power n. But since n is less than k, it will be 0. Okay, and if n is equal to k, then here we will have the power k. Yes, and after k times integrating by parts, we will get k the kth the derivative of x to the power k is k factorial, and -1 to the power k will disappear, and we will get root of the k factorial times 1 over root of 2 pi times the integral e minus x squared over 2 dx. Okay, but this integral is equal to 1. So what we showed that this integral equals to root of factorial k. And now recall that the kth Hermite polynomial is of this form. So this is 1 over root of k factorial x to the power k plus terms that are of lower power than k. Hk is orthogonal to all powers of x that are less than k. So we will have now this part. Okay, and the integral with x to the power k equals to root of the k factorial. Okay, so this will be equal to 1. So it follows that this system of polynomials is orthonormal with respect to the standard Gaussian measure. Now, one more fact that I need is that the Borel sigma field on X, it is the smallest sigma field under which all linear continuous functionals are measurable. We need this so that this implies that every measurable function on X is actually a function of some sequence of linear continuous functionals on X. To prove this, let G be the smallest sigma field on X under which all linear continuous functionals are measurable. Let's take a dense sequence in the unit sphere of X. And by the Hahn-Banach theorem, for each n, we can choose a linear functional which is equal to 1 on xn and has norm 1. Then for every element of the unit sphere, x, and for any epsilon, we can choose an element xn that is at distance epsilon from x, okay, then ln of x we can estimate as follows. As ln of xn minus ln of x minus xn. So ln of xn is equal to 1, and this thing is less than epsilon. And now if we take supremum over all n of ln of x, yes, then this supremum will be as close to 1 as we need. In other words, the norm of x coincides with this supremum. Now, if we take any open ball, let's say of center x0 and radius r, then we can write this open ball in the following form. So we see that actually this set is completely defined by a sequence of functionals Ln. So it belongs to the sigma field G. Okay. And the last thing is that since we assume that the space X is a separable space, then any open set is a countable union of open balls. This means that the smallest sigma field on X under which all linear continuous functionals are measurable coincides with the Borel sigma field. Okay, now in the finite dimensional case, polynomials are dense. This is a general property of probability measures. So if a probability measure has exponential moments, then polynomials are dense in L2. Okay, so, and from this, and from the fact that from the fact that every measurable function actually can be approximated by functions from a finite number of functionals, of linear functionals, it follows that polynomials of this form, so when we take n linear continuous functionals and substitute them into the polynomial p, so such functions will be dense in L2. Okay, so this means that Hermite polynomials of such form, the product h alpha n ln of x, they form an orthonormal basis in X. This is orthonormal basis in L2. These functions are usually split in the following way. Take polynomials h alpha for which the sum of indices alpha n is equal to k. So this is like the space of Hermite polynomials of degree k. and let xk be the closure the closure of the span of the Hermite polynomials of degree k. Then, since they form an orthonormal basis, the space L2 gamma now is represented as an orthogonal sum of spaces xk, okay, when k ranges from 0 to infinity. And this representation is called actually the Ito-Wiener expansion. So this is an expansion of the space L2 into orthogonal sequence of subspaces xk. Okay, and xk is a space of orthogonal polynomials of degree k. And since we have such a representation, we can also consider orthogonal projection on the space xk. So as an example, let's consider one-dimensional case and let f be infinitely differentiable functions such that all the derivatives of f are square integrable. In a one-dimensional case, the space xk, it is just one-dimensional space. It is the span of hk. This is the span of the case Hermite polynomial. It means that the projection of the function f on the space xk is simply the inner product of f and hk times hk. So to expand f into this sum, we only need to find the inner product of f and hk. And it turns out that this product equals 1 over k factorial, the integral of kth derivative of f. So the idea is just to write explicitly this inner product and k times integrated by parts. Okay, so the only issue is that we have like the integral over all real line. So we need to say some words why integration by parts is possible, and this is usually done using such a cut function phi, which is equal to 1 from -1 to 1, which is equal to 0 for x greater than 2, and approximate f by functions fr. So when r converges to infinity, the functions fr and all the derivatives of these functions, they converge to the function f and all the derivatives of f. For functions fr, integration by parts is possible because they have compact support. Okay, so we obtain this equality for fr and then take the limit. So in this case, we find the Ito-Wiener expansion of function f, and we see that it looks a lot like a Taylor expansion but with respect to the Gaussian measure. And also, as a next example, let's compare Ito-Wiener expansions for function f and for its derivative f prime. The inner product of f prime and hk is equal to or maybe it is easier just so let's write it like this. F prime. Here we will have exponent dx. Yeah, so now if we integrate by parts once, so, we will get here k plus 1. We will not have the derivative of f. And here we will get k plus 1. If we had k plus 1 factorial in the denominator, we will get the product of f and hk plus 1. So this means that we multiply by root of k plus 1, divide by root of k plus 1, and obtain this expression. From this, it follows that the norm of the derivative of f squared, which is equal to the sum of squares of inner products with Hermite polynomials, actually it is equal to the following sum. This is the sum over k, inner products of f and hk squared times k. And this equality allows to define the abstract analog of inner products of the derivatives. This is the so-called Sobolev space. It consists of square integrable functions for which the sum of projections squared times k is finite. Then if we consider two functions from this space D, 1, 2, we can define this functional E as 1/2 sum over k. Here we have inner product of projections of f and j, but multiplied by k. In the one-dimensional case or finite dimensional case, if we have differentiable functions f and g, then this sum, this function E coincides with 1/2 the inner product of derivative of f and derivative of g. Okay, but we defined it in the situation of a general Banach space. It turns out that in the infinite dimensional case, functions from the space D may not have even a continuous modification. And to study properties of such functions, the notion of capacity was introduced. Okay, so now let's define what it is. Let U be an open set. Then let's consider all functions f from the space D that are greater or equal to 1 almost surely on the set U. And for each such function, we can compute this thing, which is E1, it is equal to the sum of E and the inner product. So this is the integral of f squared plus EFF, which can be, as we said, this is like an abstract analog of let me write it as some kind of derivative of f squared. Okay. And take the infimum of all these expressions. Note that if this term was absent in the definition, then we will just get the measure of U. Because, for example, if we take f to be just indicator of U, then this function belongs to 2. It is equals to 1 on U. And well, its integral of this function squared is equal to the measure of U. However, such function may not belong to the space D. Okay, so the capacity of an open set shows like how well we can approximate this set by functions from the space D, which is an analog of differentiable functions. Okay, and for arbitrary set A, define the capacity of A as the infimum of capacities of open sets that contain A. It is not hard to show that the space D is a Hilbert space with respect to E1, which is actually an inner product on D. Okay, so I leave it as an exercise. And okay, so since we consider f that are greater or equal to 1, this thing is greater or equal to the norm of f squared. Okay, and if we integrate over set u, we will just get the measure of u. So it follows that the Gaussian measure gamma is not greater than the of any set A is not greater than the capacity of a set A. In particular, if a set A has a zero capacity, then it has a zero measure. But it turns out that the capacity is a finer object in the sense that it can happen that the measure of a set is zero, but the capacity is not. And let me show an example. Okay, the simplest example of such set is it turns out that in one-dimensional case, gamma is a standard Gaussian measure, the capacity of a point is not zero. So note that the measure of a point is zero, yes, but the capacity is not. So let's estimate the capacity. This is our real line, this is zero. We take any neighborhood and consider the continuously differentiable function that is greater or equal to 1 on this in a neighborhood of 0. Here, the idea why the capacity is not 0 is that such function it cannot like too fast decrease to 0 outside the neighborhood. And to make this formal, consider the segment from 0 to 1 and consider the case when the function f is greater or equal to 1/2. In this case, its L2 norm cannot be too small. I mean that if we restrict the integral from 0 to 1, then we estimate f squared by 1/4. Well, and also we can estimate the exponent by its smallest value. So this is one possible case when f is greater or equal to 1/2 from 0 to 1. And the second case, assume that somewhere here f is less than 1/2. In this case, the L2 norm of the derivative of f cannot be too small, because let this point be equal to t. Yes, because the increment of function f from 0 to t is at least 1/2. But the increment, it is the integral of the derivative of f. And this by Cauchy inequality can be estimated as the integral of f prime squared. Okay, and let's divide by root of 2 pi, multiply by x squared, multiply by exponent x squared over 2, divide by exponent f prime x squared dx. Then we need also to multiply by root of 2 pi and estimate this exponent by just root of e. And finally, increase the range of integration to the whole real line, then we will get the L2 norm of f prime. Okay, so in any case, either the L2 norm of f is greater than this constant, or L2 norm of f prime. I guess here must be 4. But we see that in a one-dimensional case, the capacity, actually the capacity of every non-empty set will be not 0. And also I would like to show an example for the Brownian motion, but to do this, I need to state some properties of a capacity. So first of all, we know that the space D is a lattice, which means that we can apply Lipschitz functions to the elements of D and get again elements of D. And mappings T such that T of 0 is equal to 0 and the increment of T is not greater than the increment of arguments. So this is one Lipschitz functions. Such functions reduce the inner product, in the sense that E1 of TF less or equal than E1 of FF. Then it turns out that the capacity of an open set U actually is attained on a unique element EU. So again, there exists a unique function EU, which is greater or equal to 1 on the set U, and such that the E1 norm of EU coincides with the capacity of U. In fact, this function EU takes values from 0 to 1 and equals to 1 almost surely in U. The function EU can be characterized as follows. So it is a unique element of the space D, which is equal to 1 almost surely on U. And such that its E1 product with functions f that are greater or equal to 0 on U is also greater or equal to 0. Okay, so if we take the inner product of EU with the function f, which is equal to 1 on U, we will get the capacity of U. Next, if U1 is an increasing sequence of open sets, then the limit of capacities of UN equals to the capacity of the union. We have the following property of capacity, that the capacity of union plus capacity of intersection is less or equal that capacity of U1 plus capacity of U2. And the last property, that if sets AN are such that the capacities of AN is a convergent series, then the capacity of upper limit of AN is equal to 0. So the property number 5, it is like a property of continuity of a measure. Yes. Property number 7 is analog of the Borel-Cantelli lemma for measures. And property number 6 shows that actually the capacity is not a measure. Yes. If we consider a measure of the union plus measure of intersection, by additivity, we will get the measure of one set plus the measure of the other set. Okay, so we don't have this property for capacity. We only have a inequality. So I will briefly discuss the proofs. Okay, so how to show the existence of this function EU. Just note that the set of functions f that are greater or equal to 1 on U, it is a convex closed set. Then we can find like minimizing sequence such that E1 of Fn converges to the capacity of U. And E1 of Fn minus Fm, Fn minus Fm. So by linearity, it can be written as follows. So this is 2E1 of F or Fn, 2E1 of Fm, and minus 4 E1 of the arithmetic mean of Fn and Fm. Now, this converges to capacity. This converges to capacity. Okay, and this part is less than minus 4 capacity of U. So this means that with respect to E1, Fn is a fundamental sequence, so it has a limit. And this limit is exactly EU. Actually, this equality also shows the uniqueness of EU. The second follows from the following inequality. So if we take this function EU, we can apply to this function the following contraction. So take minimum with 1 and maximum with 0. Then it will reduce the inner product. But on the other hand, this is greater or equal to the capacity of U, and this is equal to capacity of U. So this means that actually these two functions are identical. So U is less than 1 and greater than 0. Now, assume that function f is non-negative on U. Then if we add epsilon f to EU, it will be greater or equal to 1 on the set U. Yeah, so this means that this expression will be greater or equal to the capacity of U. So in other words, it attains minimal value at 0 at when epsilon is equal to 0. And if we differentiate in epsilon, we will actually get that the product of EU and F is non-negative. Okay, and now assume that the function f is such that f is equal to 1 on U, and if h is non-negative on U, then the product of f and h is non-negative. And I want to show that f actually coincides with EU. Consider a function g which is greater or equal to 1 on U, then the difference g minus f will be non-negative on U. Now estimate the E1 norm of g as follows. So write g as f plus g minus f, and we can expand it into E1 ff plus 2 E1 f g minus f plus E1 g minus f g minus f. And by assumption, this is non-negative, this is non-negative, so E1 norm of g is greater than E1 norm of f. This means that f is the element with the smallest E1 norm, which is exactly this function EU. Okay, and the property number 4, if f is equal to 1 on the set U, then when we take the difference of f and EU, it will be equal to 0 on the set U. Then the product of EU and f minus EU. Okay, so by the third property, it is simultaneously non-negative and also non-positive, so it is equal to 0. Then the product of EU and F is equal to the capacity of U. Okay. And probably we will finish it on the next lecture. So we will prove the properties 5 to 7, and we will show that for the Brownian motion, the property of existence of a quadratic
Okay, I suppose that this is the end for today's lecture of Georgy Ryabov.